Chapter 10 Extra Topic, Projectile Motion. This is Fort Pulaski in Georgia. It was taken over by Confederate forces early in the Civil War and then retaken by Union forces after a naval bombardment. One early use of calculus was to study projectile motion. In this section, we assume ideal projectile motion. Constant force of gravity in a downward direction, a flat surface of the ground, and no air resistance, at least usually. We assume that the projectile is launched from the origin at time t equals 0 with initial velocity v sub 0. It's launched at an angle alpha from the horizontal. If we let the initial velocity v sub 0 equal the magnitude of vector v sub 0, then we get vector v sub 0 equals v sub 0 cosine alpha I plus v sub 0 sine alpha j. The initial position is r sub 0 equals 0I plus 0j equals 0. Newton's second law of motion, F equals ma, gives us F equals m times d squared r over dt squared. That is the vertical acceleration. The force of gravity is F equals negative mgj. It's negative because the force is in the downward direction. So we set these equal to each other, and we have m d squared r dt squared equals negative mgj. So since we have mass on both sides of the equation, we can cross out mass. So the second derivative, d squared r over dt squared equals negative gj. And this is in the vertical direction. We have initial conditions r equals r sub 0 and dr dt equals v sub 0 when t equals 0. And notice this v sub 0 is a vector with direction and magnitude. Taking the antiderivative, we get dr dt equals negative gtj plus v sub 0. Taking the antiderivative again, we get r equals negative 1/2 gt squared j plus v sub 0 t plus r sub 0. Expanding, we have r equals negative 1/2 gt squared j, and we separate the velocity vector into horizontal and vertical components, getting plus v sub 0 cosine alpha ti plus v sub 0 sine alpha tj. Notice this v sub 0, as well as this one, are not vectors. They represent the speed of the projectile. And we add plus 0 at the end because r sub 0 is 0. The vector equation for ideal projectile motion then is r equals v sub 0 cosine alpha ti plus v sub 0 sine alpha t minus 1/2 gt squared j. Parametric equations for ideal projectile motion are x equals v sub 0 cosine alpha t, y equals v sub 0 sine alpha t minus 1/2 gt squared. And if you have trouble remembering which one is which, remember that cosine is traditionally horizontal, so it's in the x direction, and sine is vertical, which is in the y direction. Example 1. A projectile is fired at 60 degrees and 500 meters per second. Where will it be 10 seconds later? X equals 500 times the cosine of 60 degrees times 10, or 2,500. Y equals 500 times the sine of 60 degrees times 10 minus 1/2 times 9.8 times 10 squared, or 3,840.13. The projectile will be 2.5 kilometers downrange and at an altitude of 3.84 kilometers. Note, the speed of sound is 331.29 meters per second, or 741.1 miles per hour at sea level. Since in our problem the initial velocity was 500 meters per second, it is not really realistic to ignore air resistance, but it does make our calculation simpler. The maximum height of a projectile occurs when the vertical velocity equals 0. We have dy dt equals v sub 0 sine alpha minus gt equals 0. So v0 sine alpha equals gt. V sub 0 sine alpha over g equals t, which would be the time at the maximum height. We can substitute this expression into the formula for height to get the maximum height. Y equals v sub 0 sine alpha t minus 1/2 gt squared. If we substitute in the time at the maximum height, we get y max equals v sub 0 sine alpha times v sub 0 sine alpha over g minus 1/2 g times v sub 0 sine alpha over g squared, which simplifies to v sub 0 sine alpha squared over g minus v sub 0 sine alpha squared over 2g. If we find a common denominator, then we get y max equals v sub 0 sine alpha squared over 2g. These formulas are not on your formula sheet, but they could come in useful. When the height is 0, we have 0 equals v sub 0 sine alpha t minus 1/2 gt squared. If we factor out a t, and solve for t, one solution is 0, which would be the time at lunch. If we set the other part of the equation equal to 0, we get v sub 0 sine alpha equals 1/2 gt, or v sub 0 sine alpha over g equals t. This would be the time at impact or flight time. If we take the expression for flight time and substitute into the equation for x, we can find the range. X equals v sub 0 cosine alpha t. Substituting in, we get x equals v sub 0 cosine alpha times 2v sub 0 sine alpha over g, or x equals v sub 0 squared over g times 2 cosine alpha sine alpha. We recognize this trig identity and simplify to x equals v sub 0 squared over g times sine 2 alpha. This gives us the formula for the range. The range is maximum when sine 2 alpha is maximum. So we have sine 2 alpha equals 1, or 2 alpha equals pi over 2, or 90 degrees. So alpha equals 45 degrees. The range is maximum when the launch angle is 45 degrees. And even when you were a child, you recognize this intuitively, because if you wanted to throw a ball as far as possible, you threw it up at an angle of about 45 degrees. If we start with the parametric equations for projectile motion, we can eliminate t to get y as a function of x. X equals v sub 0 cosine alpha t, y equals v sub 0 sine alpha t minus 1/2 gt squared. Solving the left equation for t, we have x over v sub 0 cosine alpha equals t. Substituting in for t, we have y equals v sub 0 sine alpha times x over v sub 0 cosine alpha minus 1/2 g times x over v sub 0 cosine alpha squared. This simplifies to y equals negative g over 2 v sub 0 squared cosine squared alpha x squared plus tangent alpha x, which is the equation of a parabola. If we start somewhere besides the origin, the equations become x equals x sub 0 plus v sub 0 cosine alpha t, and y equals y sub 0 plus v sub 0 sine alpha t minus 1/2 gt squared. This might be a good time to note that the equations we just developed regarding flight time and distance traveled and maximum height all assume the projectile was launched from the ground on a flat surface. Example: a baseball is hit from 3 feet above the ground with an initial velocity of 152 feet per second at an angle of 20 degrees from the horizontal. A gust of wind adds a component of negative 8.8 feet per second in the horizontal direction to the initial velocity. The parametric equations become x equals 152 cosine 20 degrees minus 8.8 t, where 152 is v sub 0, 20 degrees is alpha, the launch angle, and y equals 3 plus 152 sine 20 degrees t minus 16t squared. where 3 is the initial height, or y sub 0, and 16 is 1/2 the acceleration due to gravity. These equations can be graphed on the TI-nspire to model the path of the ball. We enter the equations in parametric mode. Notice that the angle is entered in degrees. Use the pi button to get the degree symbol. Now we set up our viewing window. We assume the baseball won't travel further than 450 feet, so we set X max at 450. Because we want a realistic view of the flight path, we want a squared up viewing window. Since the height of the screen on the TI-nspire is about 64% of the width, we multiply by the width by 0.64 to get a squared up viewing window. Now we look at the flight path. Using the trace function, we see that the maximum height is about 45 feet. The distance traveled is about 442 feet. And it takes about 3.3 seconds for the ball to make the trip. In real life, there are other forces on the object. The most obvious is air resistance. If the drag due to air resistance is proportional to the velocity, we have the force of drag equals kV. Drag is in the opposite direction as velocity. Equations for the motion of a projectile with linear drag force are not part of this course.